I don't wanna grow up, I'm a curious kid. The world has 100 questions I can play with. So I'll open my arms and eyes and wonder every day till the day I die. No one really knows why gravity exists.
Welcome to Wonderfest, the Bay Area beacon of science, and our presentation of a universe of universes. This is a study of life and the cosmos, reflections on those. My name is Tucker Hyatt. I'm the founding director of Wonderfest. All right, tonight's Wonderfest speaker is Dr. Alex Filippenko. He's professor of astronomy at UC Berkeley. I have a hard time introducing Alex because he is so accomplished, and I respect him perhaps more than is healthy for me. That makes it tough to do this. Alex earned his bachelor's degree in physics at the UC Santa Barbara and his PhD in astronomy at Caltech, the California Institute of Technology. Alex almost immediately came to UC Berkeley, go Bears, driven to Cal by cosmic forces, I suspect, to climb the ladder of academia and research, and reaching its pinnacle so far as distinguished professor of astronomy and Richard and Rhoda Goldman distinguished professor in all of the physical sciences. Ooh, that's some territory. Alex's list of publications is 60 pages long, and it's in fine print. There are a lot of entries there. After presenting 1,130 papers or so, it refers to more than 2,700 less formal written contributions that, and I quote, he, Alex, doesn't bother to keep track of anymore. What is not explicitly mentioned in Alex's CV, that incredible CV, is his work as the only member of both research teams that earned the Nobel Prize in discovering the accelerating expansion of the universe. In a way, since I'd say most physicists and astronomers regard that accelerating expansion as evidence of dark energy, the man speaking tonight co-discovered dark energy. This is big. With all of that, Alex has been a phenomenal teacher and science communicator. He was voted Cal's best professor a record 9 times. And I think a very great high point of his career, he earned Wonderfest's Carl Sagan Prize for Science Popularization. Please welcome the astronomically accomplished Dr. Alex Filippenko.
Thank you so much, Tucker, for that very nice introduction. Tucker and I have been friends for decades, and I'm proud to serve on the board of Wonderfest, the Bay Area beacon of science, whose motto is truth is a great flirt, right? There you go, okay. So thank you all for coming here this evening. I know that we have some competition, unfortunately. And I was just telling Tucker that I gave a talk in Delaware on September 10th, the evening of the presidential debate. And yeah, but that did not directly coincide with the time of the debate, because my talk started at 7:30 East Coast time and the debate started at 9. But my talk started a bit late and Q&A went late, and so definitely there was some overlap. But right now, this is going on. Anyway, so thank you for coming. I'm going to talk about something more abstract than politics, the possibility of a multiverse. A universe of universes, okay, for which there is, I believe, significant circumstantial evidence, but not a shred of observational evidence, so that we can't observe these other universes. But at least one type of multiverse, I will claim, is essentially certainly a reality, and the other kinds maybe. There are many different kinds of multiverse, which I will explain, okay? So, this concept has appeared in pop culture quite a bit. It's not a multiverse, it's a copyright violation, right? Occasionally the membrane between parallel universes ruptures. Yeah. And due to a breach in the barrier between universes, Bob suddenly confronts his other self. Indeed, I will argue that in universes where even the physical laws and constants are the same as ours, if the initial positions and motions of the particles differ, as they will in different volumes, then anything that physically can happen will happen given a sufficiently large number of these volumes. And so a couple of you asked about my t-shirt today. It says, meanwhile, in a parallel universe, and the humans are acting like pigeons, and the pigeons are acting like humans. And since that's not physically impossible, I suppose, according to the laws of physics, somewhere in this vast multiverse, this may well be happening. And in an infinite multiverse, it is happening. All right, so let's start out with our universe. What do we mean? Our universe, I will define to be that part of space from which light has reached us, or can, in principle, reach us. I mean, there might be some dust cloud in the way that absorbs the visible light or whatever, but that's just a technical difficulty. So we sometimes call this our observable universe, and different physicists, different astronomers, different astrophysicists will have in mind different definitions of the universe when they're talking about the universe, and that's why I'm trying to be very careful to define my terminology here. So our universe is our observable universe, okay? All right, it's not necessarily the whole thing. The entire universe could be, and almost certainly is, much, much bigger. All right, so other universes, well, parts of the same expanding space, but too far away to see, even in principle. Light hasn't gotten here in the 14 billion years or so that our universe has existed since the Big Bang. And may even never reach us, especially given this accelerating expansion of space that Tucker mentioned that I had the great privilege of helping to discover. Okay, so that first part is relatively easy conceptually, but the second part is other universes could be volumes in some bigger hyperspace that are completely disconnected from our universe, or that budded off from it. And so even if you waited an infinitely long time, and even if the universe were not accelerating in its expansion, you could not possibly get light from these other ones because they're just entirely disconnected from ours, as opposed to this first idea that I mentioned, where if you waited long enough, and if the universe weren't expanding at an accelerating rate, but rather at a rate that's slowing down, light would eventually reach you, even though it hasn't reached you in the first 14 billion years. So this is an even wilder idea, okay? And this wilder idea is a prediction of certain quite plausible theories of the origin and evolution of our universe. But there's no way to test whether any of these theories, even if they could produce universes, are uniquely the ones, or the one that produced our universe, right? So uniqueness is hard to prove, and even if you can get other universes, it's unclear whether this is the method by which our universe was produced, because we can't go back to time less than zero, okay? This is going to be a pretty abstract talk. I'm going to really push your brains here, okay? All right. So to just start out, initially you can just say, well, this is an extension of the Copernican principle, which has served us well in science for hundreds of years. It's a plausibility argument. It's not a proof by any means, but it is a plausibility argument. So what do I mean by an extension of the Copernican principle? Well, Berkeley campus is important, but it's not the center of the universe, though we might have thought that hundreds and hundreds of years ago had we existed. We're only slightly fewer than 160 years old. Earth was thought to be the center of the universe, right, for a long, long time. And then people thought, well, maybe it's just a planet, and there are other planets, and they orbit the sun, and things aren't going around Earth. They're rather going around the sun, and ours is the third rock from the sun. All right? And then it was thought, well, maybe, okay, the sun is the center of all, the most important thing. But then people realized that the sun is just a typical garden variety star. It just happens to be very, very nearby, 150 million kilometers from Earth. So it looks bright and large. But the other stars are suns as well. And on a dark, moonless night, you can see thousands of them, especially along the plane of our Milky Way galaxy, what we call the Milky Way in the sky. And through studies of our galaxy and other galaxies, we conclude that there are hundreds of billions of stars in a typical galaxy. Oh, by the way, earlier stage, all right, you realize there are thousands of stars, millions, maybe even billions, but okay, then our galaxy is the center of the universe and all that there is. But then you realize there are other galaxies, each with billions of stars, okay? And then there are clusters of galaxies. There's a little cluster here, there's a grouping right there. Galaxies come in clusters. And our local group is a group of about 100 galaxies. It's a cluster. You could think, well, that's the center of it all. But then you realize there's the Virgo cluster. And then there are superclusters. And you might think our supercluster is the center of everything. But you look across the universe and you see many superclusters. So we go out to greater and greater distances, and we're never the center of the universe. Indeed, in an expanding universe, the subject of a different talk, there is no unique center, at least not in the dimensions that we can physically access. So that's the Copernican principle. We're never the center of everything. We're never the only example, like Earth, the sun, our galaxy, our cluster of galaxies. And so, could the observable universe be part of a plethora of such volumes, either physically connected, and so we could see them eventually if the universe were slowing down, or maybe even physically disconnected, the second type that I just described? Why not, right? It's a plausibility argument, but it's not at all a proof, okay? But here's then, bubble universes in a multiverse, right? Or one of these bubbles. And our observable universe, what I call our universe, is only a tiny fraction of one of these bubbles, right? There are other volumes you could have found yourself in as part of our total universe. But there are other universes in this multiverse, either physically disconnected in some bigger hyperspace or maybe even, budding off from one another. I'll show that in a few minutes. So there are two, actually I meant to change this to three because I added a few things to my talk just an hour or so ago. 3 lines of reasoning, at least for a multiverse, but indeed I recommend a book called Our Mathematical Universe by Max Tegmark, a professor at MIT. He was one of my teaching assistants at Berkeley a few decades ago. It's a very good book, and he discusses 10 or 12 ways you could have physically different types of multiverse, and I'm only discussing 3 lines of reasoning in addition to the Copernican principle, because I have to make this talk somewhat finite because I'm observing with one of the Keck telescopes in Hawaii essentially all night, but we're 3 hours ahead of Hawaii here, so I only have to get back to Berkeley by around 9 or 9:30 this evening. Plus I have assistants who are setting up. Anyway, the first argument is one that I personally like, but a number of physicists strongly dislike it. Although as they come to understand what we mean by it, and not to draw, extreme conclusions, they're beginning to come around to the idea. It's called the Anthropic principle. Our universe appears to be finely tuned for the development of complexity, culminating in life and intelligence as we know it in us. I'm not saying we're the epitome of intelligence. There might be more intelligent things out there, but we're pretty advanced. And a lot of things have to go right. So the universe seems to be incredibly finely tuned, and I put it in quotes because I'll explain it, for the emergence of complexity. And that complexity starts with a rich periodic table, culminating with life, especially intelligent life. So let me start with just the periodic table, because I think it's important to point this out. Sometimes those physicists who call the anthropic principle the last refuge of scoundrels, which they do, think that those of us who are supporters of the anthropic principle are focusing on our existence, that we're the epitome of it all and that the argument would crumble if it were not for us. No, the argument would not crumble, it's just made stronger by us. It appears even when you consider the rich periodic table of the elements, because as I will argue, if physical constants and certainly the physical laws were even a little bit different from what they are, the periodic table would be very boring with only hydrogen or helium or iron, and you would have a stillborn universe, one that could not develop molecular complexity, long chains of carbon atoms and things like that, all right? So even a rich periodic table requires fine-tuning. Beyond that, even the simplest prokaryotic cell is vastly complex. I mean, I couldn't take, well, I took biology and I just couldn't hack it. You know, physics is much simpler. There's less to memorize for sure. You can work things out from first principles, so to speak. But look at that thing. I mean, it's very complex. And a lot of things had to go right to make that a possibility. And then there are the eukaryotic cells with a nucleus. They're even more complex, all right? The simplest cell is much more complex than any astrophysical object. Life is far more complex than any inanimate things that we physicists have ever dealt with or ever will deal with, in my opinion. And then you have the simplest bacteria or microbes. This is one of them, roughly 1 micrometer in size, which consist of a bunch of these cells. And then you have things like slugs, which evolved from the bacteria and microbes. And then I'm skipping a few steps, but you end up with humans, with complex DNA. Of course, all life is based on DNA, and here's some of my DNA. I happen to have 4 children. But evolution led to the development of us with our advanced brains and our insatiable curiosity and our desire for the truth, or I would say the best working model of reality. I'm not sure there is such a thing as an objective ontological truth or reality, but we try to come up with the best model for how the universe works. And that's just astonishing. How many things had to go right to make this a reality? You might say, well, like what? Well, let me give you some examples of altering the physical laws a little and getting a universe that is quite boring, stillborn. And in most cases, when you do something with the physical constants, not even to mention the physical laws, you get these boring, stillborn universes, all right? So let me give a few examples, but there are many, 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 and I won't get too much into the physics. There's a thing called the strong nuclear force that not only binds the quarks together to make protons and neutrons, but binds the protons and neutrons together to form atomic nuclei. It's the strongest of the 4 so-called fundamental forces. If it were only 20% weaker relative to the electromagnetic force, which is trying to push protons apart in a nucleus, okay, you might think 20%, that's 1/5 weaker, and that's a lot, you might think, but it could have been any number. It could have been 1/4 as strong, or millions of times stronger, or whatever. In the spectrum of all possible numbers, 1/5 is quite close to 1, right? 20% weaker is not much weaker. You play around and you find out that only hydrogen is stable. All the other nuclei are unstable, basically because the protons do push each other apart because of their electrical charge, right? And the strong nuclear force isn't able to overcome that and bring them together. So you only have hydrogen, all right? No nuclear energy to power stars. They're powered by fusion of hydrogen into helium, and then helium to other elements in the later stages. No water, no carbon, or other heavy elements for life, right? Okay. How about if the strong nuclear force were a bit stronger? In this case, only 2% stronger. Then it turns out only helium would have formed in the first few minutes after the birth of the universe, this moment that we call the Big Bang. No hydrogen. All the hydrogen, all the protons and neutrons would have come together and formed helium, or almost all of them. So you might get stars, but they'd be short-lived stars, helium fusion to carbon and oxygen and things like that, which doesn't last very long. And some of those might blow up and make some of the heavy elements, carbon and oxygen and things like that, iron, calcium, fine. But without the hydrogen, you don't have hydrocarbons, you don't have water, you don't have, lots of things that require hydrogen in our lives, all right? All right, here's another argument. Suppose the neutron were somewhat heavier than it is, and here I don't give a quantitative number. It's a bit tricky to figure out. But if neutrons were somewhat heavier than they are, and right now they're only about 2 electrons heavier than protons. Protons and neutrons are each about 1/2000th of an electron. So electrons are very light, not much mass at all. A neutron is only 2 electrons heavier, more massive than a proton. But if a neutron were somewhat heavier than it is, then neutrons would basically quite quickly decay into protons. As it is, a free neutron sitting on a table decays after about 15 minutes. But if they were heavier still, they would be more likely to decay. And in the early universe, they would have decayed into protons and none of them would be left. And depending on exactly how much heavier the neutron is, even nuclei wouldn't be stable. And there it's a bit tricky because though a free neutron would decay much more quickly if it were more massive, you could argue that with the strong nuclear force, yada, 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 neutrons and protons could be made stable in nuclei, and so that's where it gets complicated, okay? But it would basically not have elements heavier than hydrogen if the neutron were somewhat heavier than it is, okay? So that's pretty bad. All right, what if the proton were just 0.2% heavier than it is? By the way, I'm just giving examples, and there's no quiz at the end here. I'm giving a midterm in my class a week from Friday, but even they don't have to memorize all these arguments or the exact numbers. But if the proton were just 0.2% heavier than it is, then it turns out protons would decay into neutrons, and atoms wouldn't exist because you need the protons as well. They're the ones that hang on to the electrons in a stable atom. So only a narrow range for the relative masses, neutron to proton mass ratio, results in an interesting universe. And I could have started by saying, let me tell you some of the things that you could alter, and I could say I'm going to start with the relative masses of the neutron and proton, and you'd say, oh, yawn, boring, maybe I should turn on my phone and start watching the debate. Why are you going to talk about something as boring as the relative masses of the neutron and proton? The ratio is nearly 1. Who cares exactly what it is? Well, my point is that if it were outside a very narrow range, a rich periodic table wouldn't even exist, let alone prokaryotes, eukaryotes, bacteria, microbes, slugs, humans, us, So to the physicists who claim that people like myself are focusing too much on us, the anthropic part, the focusing on us, I'm saying, no, just go back to the periodic table. It's much deeper than that. I'm not focusing on us, okay? All right, there are many examples of this. All right, so in this line of reasoning then, what can you conclude? Well, I can think of 3 reasonable possibilities. One is that there's only a single universe. It's special. A divine creator tailor-made it for us. That is a reasonable deduction. There is no scientific argument that disproves this hypothesis. And I object to those scientists who try to pit science against religion and say that they have scientifically proven that God does not exist. Nor do I like it when scientific creationists try to use science to prove the existence of God. They are mutually exclusive lines of reasoning in the sense that you can't use them to prove or disprove the other. Okay? You just can't. And for hundreds of years, we've been trying to quell and even quench the discord between science and religion. That, all of us know the story of Galileo and how he got off easy under house arrest compared to his contemporary Giordano Bruno, who was burned naked at the stake in Rome in the Garden of Roses for believing various heretical ideas such as the stars are other suns, and some of them may even have planets, and some of those planets may even have life, and that was very objectionable to the Inquisition and stuff, and so they burned him, So that was bad. But it's also bad to try to say, oh, we scientists know it all, and there isn't a divine creator, and anyone who thinks there is just some sort of a dummy or something. No, there's no way I can disprove that. But there's also no way I can prove it. And so, since this is a talk where I will try to stick to science as much as possible, I will henceforth no longer consider this hypothesis, not because it's necessarily wrong, it isn't necessarily wrong, but because I can't go anywhere with it. It's a dead end from a scientific perspective. But you are welcome to believe anything you want. And this is not an unreasonable belief. Indeed, in biology, this idea is often used as, almost like the divine watchmaker, although a watch is not a biological thing. They point to the various cells in the bacteria and they say, that's so complicated, how could it have arisen by chance? Maybe it didn't arise by chance. And I won't tell you what I believe, because it's irrelevant for the rest of this talk, okay? Okay, so this is a form of what in particular biologists call intelligent design, an argument for God. All right, fine. What's another possible implication? With or without God, okay, right? There's one universe, it's special, just happens to be just right. That's the way it is, either by accident or by design, but I already considered that first possibility in my first possible conclusion. So since I've now removed that one, it's just right for us by accident. It's possible. I personally reject this hypothesis because the odds against it, if you'll pardon the pun, are astronomical. Right? There's one universe. And it just happens to be this way. It's like you're playing poker for the very first time, and you have 4 of a kind, or a straight flush. And meanwhile, I have a pretty darn good hand too, so I'm betting away, and then you beat me with this incredible hand, and it's your first hand ever in poker. It's possible by accident. But I will suspect that you have a deal with the dealer. Like in the movie The Sting, right? You don't want me to have like Jack High or some crummy hand, because I'm not going to be betting a lot. You want me to have a full house or something, and you have 4 of a kind, right? Or you want me to have a 4 of a kind and you have a straight flush, right? You want me to be betting away. It's very unlikely, exceedingly low odds. Poker example, right? But it could happen. It could happen. I cannot reject this possibility completely, but I reject it probabilistically, right? So, third possibility, emphasizing again, with or without God. There are multiple universes spanning a wide range of physical properties. Most of them are boring. Most of them don't have a rich periodic table. We are here, so we necessarily live in one of the good ones. Not necessarily the only good one, not necessarily the best possible one, but a pretty darn good poker hand. A rare one compared to the many, many more uninteresting universes, Jack High type universes, right? I've won on Jack High, by the way, occasionally. When it gets to heads up, right, you only are against one other opponent, so what are the odds that they have a great hand? That's interesting, right? There's a cosmic archipelago of universes spanning all possible properties, and we are around, so we live in one of the good ones, necessarily. One of the other reasons that some physicists object to the anthropic principle is that they think that people like myself are saying the universe exists so that humans can exist, so that complexity can exist. No, I'm not saying that. I'm saying there's a bunch of universes. Given our existence, complexity, we are necessarily in one of the good ones. But they were not created so that we exist. There's no teleological type overtones here, right? Because again, those physicists are trying to not mix science and religion. So they're saying, oh, you're being religious here. I'm not. I'm just saying that there's a bunch of them, all right? So in this sense, our universe is finely tuned for our existence. But I put that in quotes because this is special universe is not unexpected among this plethora of universes in the multiverse. At least one or a few of the universes would have been suitable if there are enough universes spanning enough physical properties, you know. Or again, given our existence, it's an existence proof. We exist, therefore at least one of them was suitable for the development of complexity, culminating with, as far as we can tell so far, life as we know it. Although we will soon perhaps be replaced by silicon-based life that's even more intelligent, and that's happening much more quickly than I anticipated. Anyway, like playing poker. You can see I like poker. You play enough hands and you're going to get a four of a kind every once in a while, or even a straight flush. I think the best I've ever done is a four of a kind. I don't think I've ever had a straight flush. With that Texas Hold'em, I once had pocket jacks, and then the first two cards of the flop were jacks. Yeah, all I needed was four cards, and I already had four, whatever. Okay, so here's an example of this line of reasoning. The ancient Greek philosophers could have, and there's evidence that some did, think about what is it that makes Earth so darn special for life, for butterflies and newts and foxes and humans? What is it fundamentally that makes it this way? And they could have thought about this issue until they were blue in the face and not come up with a reasonable answer, because you know what? There is no reasonable answer. Or they could have, and some even preceding Giordano Bruno apparently did, think about the possibility that, well, gosh, maybe the stars are other suns, and maybe there are planets around them with different masses and different atmospheric compositions and different distances and et cetera, et cetera. And some of them, most of them, are not hospitable, and some are. In our own solar system, you know, one is Earth, but Mercury isn't. It's too close to the sun. And Neptune isn't. They didn't know about Neptune, but you get the point. Even Saturn is too far away. They knew about Saturn, the ancients did. And then extrapolating to other stars. What if there are trillions of planets having a vast ranges of masses and distances from their host stars and atmospheric thicknesses and compositions and so on and so forth? And most of them are boring in terms of their ability to lead to the complexity that we know of as life. But given enough of these planets, at least one, Earth, had the right conditions. So they could have suspected strongly from this line of reasoning that though there were only, at that time, only, Mercury, Venus, Earth, Mars, Jupiter, and Saturn were known, you need a lot more to have an ensemble. So they could have speculated quite reasonably that for this argument to carry any weight, there's got to be millions, billions, maybe trillions of these things out there. That is, circling many, many stars having a much broader range of properties than what is sampled only in our own solar system, okay? And then among that vast multitude of objects, let's call them planets, occasionally there will be some that are hospitable to the development of life. And we were among the lucky ones, right? Now, fast forward to 2024, and we know of thousands of exoplanets. The Kepler satellite found thousands of them. Now TESS is finding them. Ground-based studies of the Doppler wobble technique finds them. I mean, we know now that most of the stars that you see in the sky actually have planetary systems. You can play a statistical argument based on the transit method and stuff like that. They may not all be easily detectable, but they're there, all right? So you would have reasonably concluded the existence of exoplanets, and you would have been right. Thousands of years later, you would have been shown to have been right, although it was only a plausibility argument at the time, based on this, in a sense, this principle that there is no fundamental reason Earth is the way it is. It's just got a particular set of properties among a bunch of random variables, or variables that could have had a random set of values. And those other planets are just not conducive to the development of what we call life. Okay? So that's the anthropic idea, and I find it quite reasonable, actually, but not a proof. Okay? So then, here's some independent physical reasons for expecting a multiverse that most conventional physicists start at least listening to more than anthropic reasoning. Sometimes they just turn off if they smell anthropic reasoning. Less so with time, I'm finding, but many are still turned off. But then you start giving some other physical reasons, and they start paying attention more. And it leads to the same conclusion. Okay. The universe may well have been what we call a quantum fluctuation out of nothing, all right? We know that particle-antiparticle pairs appear for short amounts of time out of nothing and then disappear and create nothing. So time is going along the horizontal axis here, and I plot, there's nothing here, and then suddenly there's a neutrino and what we call an antineutrino. Nothing here, and proton and antiproton, but then they disappear. Electron, positron, anti-electron. They appear, and then they disappear, okay? This is a quantum violation of the classical law, quote unquote, of conservation of energy. It's not that the proton has positive energy and the antiproton has negative energy, and so they add up to zero. No, both the proton and antiproton have positive energy. So you've created positive energy out of nothing, but only for a very short time. And quantum mechanics not only allows that, it demands it. It's happening all the time in the space between us, within the atoms of which we consist. And though no single virtual particle can be directly detected, that's why they're called virtual, their collective action in certain circumstances can and has been detected. For those who want to learn more about this, you can look up on Wikipedia, for example, the Casimir effect, Casimir, or the Lamb shift, as in the animal, but it's after a person whose last name was Lamb. These are all very, very subtle measurements that show that collectively these quantum fluctuations have an effect on physical reality. So they do exist. They're a fundamental feature of what's called quantum electrodynamics, all right, for which Richard Feynman and others won the Nobel Prize in Physics, I think, in 1964 or 65. Well, it turns out that if you already have a space in which there are laws of physics, and that's a big if, that's why we have to kind of kick the can down the road, right? You can say, as some physicists say, all we need are laws of physics, so we don't need God. But then you could argue with them, well, what produced the laws of physics? Isn't that a God? And they say, no, they were just laws of physics. And then they may object, saying laws of physics have to have a creator. And then the physicists could say, well, but then a creator has to have a creator. And you just end up kicking the can farther down the road along both sides, right? You can't come to a testable hypothesis, all right? But there are books that basically say all you need are the laws of physics and we can do away with God. Fine, maybe that's true, but maybe God created the laws of physics, or maybe the laws of physics are God, right? All right, whatever. So you have a universe, or you have a space, or something in which there are physical laws that give rise to these fluctuations. It turns out that if you have a sufficiently long-lived fluctuation, and it has the right internal properties, I mean, most of these will go away, but under the right conditions, an idea called inflation can take over, okay? Inflation is the early postulated exponential growth of our universe from something as tiny as you want to something arbitrarily large, depending on how many doubling times you have. It's an exponential growth of one particularly long-lived quantum fluctuation that allows this baby universe that's as small as you want it to be to grow to an arbitrarily large size. Inflation just does that. It's the ultimate free lunch, as Alan Guth of MIT likes to call it, because you start with zero energy. It's a quantum violation of the conservation of energy law, but quantum mechanics violates all kinds of things in classical physics, so that's okay. And then the growth of this universe, for reasons I won't go into in any detail, either maintains conservation of energy, that is, it's just zero still, plus or minus that quantum fluctuation, or in general relativity, you can argue that conservation of energy isn't even a law, quote unquote, in general relativity. I prefer to think of energy being conserved because there's an argument I can use where I can show you mathematically that under reasonable assumptions it is conserved. And then some of my general relativity pundit colleagues say, well, that's a flawed argument. You can't really use it. And then I say, yeah, but then energy isn't conserved. And they go, yeah, but that's okay. In general relativity, yeah, don't stone the messenger. In general relativity, energy is not necessarily conserved, okay? So anyway, so you get a universe out of nothing, basically. The ultimate free lunch, Alan Guth calls it, right? Echoing Milton Friedman and others who claim there is no such thing as a free lunch. Well, the universe may have been one. And if it happened once, then why not multiple times? What would prevent it from happening over and over and over again, right? Quantum physics and this idea in cosmology called inflation suggests that this is quite reasonable, all right? And although inflation hasn't been proven, there are certain observations of a cosmological nature of the universe on large scales that support the simplest forms of inflation theory. One criticism of inflation theory that is valid is that it's tunable enough that almost anything that we observe could be explained by some form of inflation, which is why some physicists do not like inflation almost as much as they don't like the anthropic reasoning, because they say that if a theory has too many tunable parameters, then it has no explanatory power in the sense that you can't falsify it. You can't say, okay, if I make such and such a measurement and it doesn't work out the way you predicted, you can toss that theory out, that hypothesis out. That's what we mean by falsifiable. And in science, that idea of falsifiability is a very important one. So I'm sympathetic to those who have criticisms about inflation for those reasons. I worry. On the other hand, inflation is a very beautiful idea, and a number of observational constraints are satisfied by the observations that we have made. And so I kind of like inflation, but I acknowledge that there are potential problems with it. Okay. Well, so here then are these independent quantum fluctuations in some bigger hyperspace, although mathematically it's not even necessarily the case that there is this bigger cube. In some sense, you just have these volumes occurring where I don't know where, and that's why I like to draw a cube around them, some bigger hyperspace. But in the mathematics of it all, you don't even really necessarily need that bigger hyperspace, which makes my head hurt. So I'm going to draw the cube, okay? And then Andre Linde at Stanford has another variation of inflation where he says it's the gift that keeps on giving, once you have an inflating volume, it's extraordinarily difficult to make all of it stop inflating. You can make it stop inflating in certain places, but other parts will keep on inflating. And so in that sense, then, mother universes give rise to baby universes, either because inflation stopped nearly everywhere, but not there, and not there, and not there, or it stopped everywhere, but then new quantum fluctuations can make new universes bud off and inflate. And in some hypertime, in this hyperspace, hypertime is going upward, and here are all these universes, and this is by no means the first one. This was the child of some other universe, and it's a never-ending process. Chaotic, eternal inflation. It's just very hard to stop it. Given infinite time, it produces an infinite number of universes, especially since you go back in time some infinite amount. Again, this makes my head hurt, right? I told you this would not be an easy talk. If you thought this was just going to be casual entertainment and stuff, you came to the wrong presentation, okay? And you may have noticed that both in this picture and in this one, I drew these little bulbs. I didn't actually, I stole these things. Actually, this one I made. A friend of mine made it for me. But this one Andre Linde drew, or an artist drew it for him, or now you can have the AI doing it. But we make these things have different colors. And the reason for that is that they may have different values of the physical constants. We don't know why the physical constants, like the speed of light, or more fundamentally, things like the fine structure constant, which is the charge of the electron squared over something called Planck's constant, the quantum constant, divided by 2 pi, all divided by the speed of light. The reason I mentioned this thing, alpha, is that it's dimensionless. It doesn't matter which units you use, the units cancel out. It's 1 over 137 in our universe. It dictates the structure of atoms and stuff. It's one of these constants that if it were different, atoms basically wouldn't exist, or they wouldn't bind together or whatever. You can argue that the speed of light, depends on what units you're using already. And so when we talk about the value of the speed of light being different, you can make it different through different units. But fundamental constants you can't make different from a different set of units. They're just a number, okay? And so we don't know why the fundamental constants have the value they do, but if they didn't have the value they do, like the ratio of the proton and neutron masses, the grams cancel out, right? So that's a fundamental constant. The universe would be very different. So they could have different fundamental constants, since we don't know what dictated that, or even more radically, they could have different physical laws. Maybe there's more than one mathematically self-consistent way to have a bunch of physical laws. Okay? So, that's pretty amazing. Physical laws could differ in the various universes. String theorists, which I hope I'll have a chance to mention at the end, working on fundamental physical so-called theory of everything, where they unify quantum mechanics and gravity, the two great pillars of modern physics. They claim that there may be what's called a landscape, you can look this up, that's the term they use, a landscape of 10 to the 500 power mathematically self-consistent universes. They're the greatest multiverse proponents now, if anything. When I was a graduate student in the early 1980s, late 1970s, string theory was just starting, and I'm exaggerating a little bit, being overly dramatic, but they would pound themselves in the chest and say, we're so smart, we're going to figure out the one way God could have made the universe in a physically and mathematically self-consistent manner. Now, 45 years later, they've done a complete about-face, and they say, you know what, there are 10 to the 500 power different possible kinds of universes, this landscape. So they're among the greatest proponents of the multiverse idea. And I stuck that in case I don't have more time to say more about string theory. But if different laws bother you, then at the very least different constants, as I just said. They may be accidental, maybe not. Maybe there's one way they could have formed, and it just happens to be this special way that allows long, complex chains of carbon atoms and things like that. Again, that sounds pretty far-fetched to me, but it's not impossible. Okay? Neutron to proton mass, etc. So the example I give here is the snowflake, all right? So based on the H2O molecule, right, oxygen and 2 hydrogens at an angle of 105.7 degrees, not 120 by the way, they form hexagonal structures, and hexagons have angles of 120, not 105.7. So it's not immediately obvious how a bunch of water molecules form hexagonal structures when frozen. Turns out they're in slightly different planes. But snowflakes all have a hexagonal symmetry if they form without being hassled by intruders and stuff, all right? And Ken Liebrecht at Caltech has taken these amazing photographs. So there's this hexagonal symmetry fundamentally. But no two snowflakes are absolutely identical, all right? And the slightly different shapes are functions of the positions and momenta, the motions of the molecules at the moment that crystallization started to occur. And that then is a function of the temperature and humidity of the little pockets of air and stuff like that. And so within the physical dimensions of a snowflake, a pocket of air will have essentially the same water content, humidity, and temperature and stuff. In very different regions, they'll have different temperatures, humidity, density, all that kind of stuff. But over the region of a snowflake, the values are reasonably constant. And so what happens is you get these different shapes that are a function of just accidents of nature. The positions and motions of these molecules of water that are dependent on temperature and humidity and density and stuff, okay? And those we would claim, most of us, are relatively boring. Who cares what the exact humidity and temperature was and all that? Ken Liebrecht studies snowflakes. He doesn't find it boring at all, right, to understand their structure and all that. But to most of us, the most interesting thing is the fundamental hexagonal structure. That's what water molecules form. And oh yeah, they're slightly different shapes. Fine. They're pretty to look at under a microscope. The constants of nature may be analogous to the shape of snowflakes. Random, not dictated by anything fundamental. That's the idea, okay? So, these different universes could have even different physical laws, or if that bothers you, different physical constants. And with enough of these universes, you then have the desired ensemble that spans the full range of allowable properties. And so then occasionally you're going to get a good universes, right? Either in this picture or that picture. And then string theory, just very quickly, well, let me just say it. All fundamental particles are different vibrational patterns in a little unit of energy called a string or a membrane. The point is, they're not points. They are one-dimensional or multi-dimensional membranes, and they're flopping around, and they're like musical notes. Different vibrational modes give you the different particles, neutrinos or whatever. And for the math to work, you need 10 and now 11 dimensions. Well, we know about X, Y, Z, and time, but there are 7 others, okay? And most we think are wrapped up on tiny scales, 10 to the minus 33 centimeters, what's called the Planck length. And if you were like a bird flying over sandpaper, it would look two-dimensional to you, but you swoop in and you look through a magnifying glass and you see that there's granules there, but it looked two-dimensional to you from far above. So we don't see these little dimensions that are 20 orders of magnitude smaller than a proton, but they're there, and they may have various shapes, thousands of possibilities, for each choice of the number of tiny dimensions. There are curled up spaces at every point. They're called Calabi-Yau spaces after mathematicians who studied this branch of mathematics, not in the context of string theory, but in the context of just mathematics. And so who knows what they look like, right? We can't diagram them. But at every point, there are all these curled up 7 dimensions in string theory, okay? And this then, if you take all the combinations and all the way this can happen, and all, not necessarily 7 small dimensions, some of them could be big and all that, that's when you do this and you come up with this landscape of 10 to the 500 power universes, okay? So that's all I'll say about that. But that's sort of the third argument, right? There was Anthropic and inflation and multiverse and quantum fluctuations and then string theory. So all these arguments point to an ensemble of universes with different properties. Our universe is a good one. It may be just one island in this cosmic archipelago of universes, most of which are pretty boring. A few of which may be more interesting, maybe vastly more interesting, okay? It's a seemingly special island, but its existence isn't unexpected. So that's the argument. Now, do other universes based on inflation or string theory or the anthropic reasoning exist? Few, if any, ways to find out for certain, at least right now. I say few, if any, because it's conceivable that one of these other universes could collide with ours, and then that would cause an imprint in the radio radiation that we call the cosmic microwave background. But it's also much more likely that the space in that bigger hyperspace where I had all those multicolored bubbles expands, if anything, faster than the other regions, because those parts in between the bubbles are still inflating. So it's more likely that they'll never collide. But they could collide, and so there is a possibility that we could find the signature of another universe. No one's found one yet, all right? Maybe there's some way to have a wormhole that connects our universe with some other universe, right? You've heard this idea that if you go into a black hole, you travel through a wormhole and you might end up in another part of our universe or in some other universe. I think Max Tegmark has a chapter on that, maybe not. But yeah, there could be some way maybe of testing for their existence, but I'm pretty skeptical that it will ever be a testable hypothesis. And this is where I am a bit uncomfortable with it. But it's not like we wake up at 3 in the morning and to go to the bathroom and say, oh, let there be a multiverse. Wouldn't that be cool? The arguments are much more physically based. They are scientific. It's just that the conclusion by its very nature, at least temporarily and maybe permanently, removes itself from being strictly within the realm of science. But it's not that we just came up with this stuff because it sounds interesting. There are these reasons that I hope I articulated reasonably clearly. Summarizing here, the multiverse is a logical possibility that is based on science, yet by its very nature is at the periphery of science, at least temporarily and quite possibly permanently. So those ones with different laws and different constants, those are truly weird and stuff. Let's get back to the one where it's just one inflating volume, and then inflation maybe continued, but in our part of the universe it stopped, and then stars eventually formed and light started coming toward us, and we have our observable universe. But there are other observable universes within this overall single expanding mass, right? All with the same laws of physics, all with the same physical constants. It's just, it went whoosh, and then the whooshing stopped in various places and regular expansion took over. It's like the launching of an apple or this clicker. And they're only different in terms of their initial positions and motions of the particles. But the laws and constants are the same. So then it's like throwing one die, or 2 dice, or 52 cards, right? With 52 cards, there's a lot of poker hands, but it's not infinite. With one die, there are only 6 possibilities, right? So these other ones are exceedingly far away, and are, by parallel, often people say, okay, there are these other ones, but if they're totally different looking, then they're not parallel, even though they sort of are. But often people are thinking that by parallel universes, they're saying, you know, we're sitting around somewhere having this very same conversation, basically. With small differences. I decide to scratch my head. Or you think I'm such a weirdo that, you know, you're just going to punch me in the face. Or you won't do that, but you'll walk out of the tavern or something, right? Things that are close to being indistinguishable from our own. Well, those are very far away, okay? They are not visible to us. They're very, very far away. But you do have this gargantuan inflating space with the same physical laws and the physical constants throughout, and life probably occurs in some of them. Our own universe is just our observable part, but many, many other distinct universes beyond our observable horizon exist, and they're independent of ours. They have different positions and motions of those particles, okay? So in that case, If there's enough of them, anything that can happen will, right? Well, how likely is this? There are observations of the cosmic microwave background that strongly argue that the total universe is at least 100 times bigger than our observable universe. Okay, and other cosmological, slightly more indirect pieces of evidence that suggest that the total universe is at least 100,000 times bigger than ours. 100 times the volume or 100,000 times the volume, if that's all there is, folks, there isn't a universe where we're sitting around having essentially the same combination. It's not enough poker hands, okay? But, if inflation continued for sufficiently long, maybe even didn't stop overall, but continued stopping in various subsets, then you could have an infinite number of independent observable volumes, in which case we are sitting around somewhere having this same evening, or slightly different, okay? To take that argument a bit further, some are exact duplicates of us, and so you get these various cartoons where the cartoonists knew of this concept. You are unique in all the world, that is, unless there's a parallel universe and we all have doubles, okay? The mother saying to her child, knowing a little bit too much physics. And there are ones that are somewhat different from ours. They have the same physical laws and constants, but not the same history because they started out a little bit different, okay? So, as I said, anything that possibly can happen does happen. So here's a cartoon. My wife believes I have a girlfriend in one of the parallel universes. Well, you do! But guess what? She has a boyfriend, too. Or whatever her preference is, you know. So, yeah. And somewhere I'm this terrible person. I'm going to go at the end of this, I'm going to punch all of you in the face. But it's not my fault. It's not Alex Filippenko, even though for all intents and purposes it acts like me in all other aspects of life. But I can't blame myself in this universe for it, because that's not me. That's not what I'm going to do in this universe, okay? Even if you don't support Wonderfest at the end of this talk, okay? So, and please do. It's a great organization. In the alternate universe I've come up with, everything would be exactly the same, except cats would bark. Okay, and this goes back to my thing that we're the pigeons and the pigeons are the humans, right? David believes in multiple universes, all of them lousy. Okay, so he's a pessimist. All right? Somewhere in an alternate universe, you're mine, the giant mouse says to the cat. Very reminiscent of this t-shirt. So as I said, I'm a very bad person in some of them. But so are you, okay? So, there. Ebenezer, I'm the ghost of Christmas future, from an alternate universe where you're an awesome guy. So, not much to say, really. I love it when cartoonists know some physics, you know. Okay, so then why should any universes exist? Well, we don't know, and almost certainly will never know, right? Science alone cannot provide all the answers. No realm of human thought or reasoning can provide all the answers alone, and probably not even all together, right? So in the end, believe what makes you comfortable. But we do live on a really amazing Earth, part of many, 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 many planets, a random one. And I am strongly of the opinion that our observable universe is part of a multiverse. Certainly the one where it's just an observable volume in a much bigger space. As I said, we have direct observational evidence, even though we haven't seen photons from beyond our universe. It's a subtle argument having to do with the cosmic microwave background. It's at least 100 times bigger, quite possibly at least 100,000 times bigger. And very few physicists would object to that limited definition of parallel of the multiverse. if you start talking to a physicist and they immediately object, explain to them this one, this big inflating volume, and maybe if it's not even inflating, but at least it's a bigger volume than what we can see. And the particles have the same laws of physics and blah, 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 but they're just moving in different ways. So there will be different combinations, different histories of the universe. And if there are enough of them, maybe even we were recreated somewhere. But that's a big if, but at least different histories among 100,000. Those are universes in a multiverse. That's just the simplest kind. And I would really challenge any physicist to a debate, or a duel with swords, whatever, on how they could argue against that simplest multiverse. The other bubbles and inflation budding off and all that, there we have no direct evidence for sure. And it's certainly more speculative, but I think it's quite likely, because the problem with the universe that's the same as ours, just different initial conditions, is that doesn't explain the proton to neutron masses and the fine structure constant and all that. For that, we need the multiverse with different physical constants, if not different laws. And that's why I go beyond just the simplest multiverse. The simplest one is what Max Tegmark calls the level 1 multiverse. The one where the constants are different are level 2 multiverse. There's a thing called the many worlds interpretation of quantum mechanics, Everett and Wheeler, which is really weird. I'm not sure I subscribe to it, but that's the level 3. And then there's level 4, where the mathematics is just completely different and all that. So you might read Tegmark's book. So I have a few more minutes, I just wanted to mention that I'm part of the University of California, which owns and operates Lick Observatory, which has been conducting science since 1888, 136 years, right? Pretty amazing. And it's not just the old refractor that some of you have visited, and there used to be a 12-inch refractor there, with which I did my first research project as an undergraduate at UC Santa Barbara. But we now have bigger and telescopes equipped with modern instruments that are doing all kinds of things, searching for other Earths with the 2.4 meter automated planet finder, and searching and following up on exploding stars with a telescope that I run, the Kate telescope, that finds these exploding stars. Takes a couple of weeks to brighten and a few months to decline, but so as not to bore you, my colleague Peter Chalice has sped up the process. I have undergraduate students who look at the candidate supernovae that the software, the AI finds, and then they use their still slightly superior eye-brain combination to vet the candidates. I'm sorry to say that within a few years I might not need undergraduates anymore. But you might not need professors pretty soon either. So, white-collar workers are being threatened now. But anyway, they get their first taste of research, and most don't become professors of astrophysics. They became employees of Microsoft or Google or Apple or whatever, but they use their skills at logical reasoning, programming, data analysis, mathematical preparation, physical intuition, and all that to be really very valuable employees at those companies. And some become professors of astrophysics. And they use the 1 meter nickel telescope to follow the exploding stars as they brighten and fade and find exoplanets. One of my undergraduates just published a paper on exoplanets. And then we use the 3 meter telescope to obtain spectra of exploding stars. We pass the light through a prism and study the chemical composition and all that kind of stuff. So amazing science, even from a light polluted area, right? We've got the whole Bay Area to contend with. We're not going to see the faintest objects in the universe, but we can tune our science to focus on bright things that are not so affected by city lights. Plus, we give students an opportunity to get trained and to submit proposals of their own. We're a public outreach institution, and we develop technology. So we do all these great things, and students now observe from campus observing rooms throughout the University of California system. So we have all these great things that we're doing, but University of California funding is very low, especially after the pandemic, and uncertain for the future. A decade ago, the UC Office of the President threatened to, in fact, they said they would close the observatory by 2018. And I and a few others did a big rabble-rousing and got the public interested and got some donations. I got one from Google and stuff. We kept it alive, but you know, we're no longer existential, as in a year-to-year type thing, but over the long run, it is still existential. And it's harder to get, in fact, I've not been able to get renewals from companies like Google. It's no surprise to many of you that tech jobs have been cut throughout the Bay Area a lot, and a lot of the perks at some of these companies have gone away and stuff, and so they're just not in a giving mood right now. The CFO of Google in particular is most interested in the shareholders, and there's some validity to that line of reasoning, but there's also validity to supporting science outreach and development of young scientists and future Google employees, but I've had a hard time making that argument stick. So, you know, you can give your tax-deductible contribution to Lick Observatory in many ways, directly to Lick, or through a fund that I set up at UC Berkeley called the Friends of UC Berkeley Lick Observatory, and I have some control over how the money is spent. And no contributions are too small. Large contributions are, of course, even better, but the more the merrier, and it also helps having lots of people contribute, because then we can show the Office of the President that there are a lot of people who support us at a low level and a few people who support us at a higher level, but that community involvement is very important. So no pressure at all, and of course do what you want, but this is a very good organization to which to give, as is Wonderfest. So thank you very much, and I do have time for questions, and I'll be very happy to entertain as many questions as you. Thank you.
Would you mind repeating the question?
And I'll certainly repeat the questions, yeah. Yes, go ahead.
In the example of, I think it was the chaotic eternal universe.
Yeah, the chaotic and eternal inflation. Mm-hmm.
Yeah, and then so the bubbles are still kind of like stuck to each other through these, you know, channels.
Okay.
Could those be wormholes?
Yeah, so the question is, in the chaotically inflating universe, where I had the mother universe down here, not necessarily the first one, and there were all these branches, they're connected in that the subsequent universes budded off, in a sense, from the mother universe, either as a quantum fluctuation within it that then started expanding in completely separate dimensions, I forgot to mention that, or they are regions that kept on inflating, but the rest of the universe stopped inflating, okay? But we don't live in one of those still inflating things. We live in the one down here. But with some super cosmic time, that was the arrow going upward, as you go upward in time, there are these ones that bud off, and they're elsewhere. We can't reach them. And so you asked, are they connected through wormholes? Not really, because in a sense a wormhole connects one universe to another right now, whereas those were things that budded off as the mother universe aged. And I suppose you could think of the budding sequence as, well, they're still connected in some way, but since you can't go backward in time, things up there will never go back to where we are here. And because the inflation stretches space faster than the speed of light, and that is not a violation of relativity, it turns out, from where we are here, we can't get into one of those regions that budded off. So in that sense, it's not a wormhole. Though I can see from the diagram and even some almost mathematical correspondence, I can see why one might reasonably be led to think that way. But it's different from what we conventionally think of as a wormhole.
Yeah. They budded off, but they didn't pinch off.
They budded off, but they didn't pinch off, right.
And so that part that's still connected.
Yeah, they're still connected, but they're not connected in a causal way.
Okay.
From here to there.
All right.
Right. It's the causality thing. Can you get from here to there? It's a little bit like going backward in time. The problem with that is that if you do that, you could prevent your parents from ever meeting, and then you would never have been born. But then how would you have made the journey to prevent them from meeting? Violations of causality, cause and effect, are taken very seriously by physicists. However, I hasten to add that it's never been proven that causality can't be violated. Yeah, so I saw some other hands up. I'm sure. Yes, go ahead.
Yes, I've often heard that with the Buddhist cosmology of sunyata and emptiness, that quantum physics kind of meets and helps explain it. And I
Yeah.
wonder if you could, appearances arising out of nothingness, but yet connected.
Yeah.
So I'd love to hear.
Right, in Buddhist philosophy, the universe arising out of nothingness yet connected. Another aspect, I think, of Buddhist philosophy, although I'm by no means an expert, is a cyclic universe. It expands for a while, recollapses, and goes on forever, like never ending. I think that's an aspect of it as well. So, I mean, there are a lot of such things where in various philosophies, ideas were conjured up with no physical or mathematical basis. But it turns out they're ideas that could be grounded in physics and in what we call reality. But those are, in a sense, lucky guesses. Sometimes people say that, oh, well, in the Quran or in the Bible or whatever, they predict this and that. Enough documents say enough things that sometimes you just kind of have a lucky guess. And not to denigrate any of these philosophies, and in particular Buddhist philosophy, which was what your question was. I'm, without knowing, strictly speaking, how they came to their conclusions, so I will preface my remarks by that, I'm going to venture to say that it was a lucky guess. And moreover, it may not even be true in terms of the cyclic part. There's no evidence right now that the dark energy is going to change sign and then cause us to recollapse. It might, but even if the universe recollapses, there's no evidence that we will reemerge. So the cyclic universe isn't even something that is a favored thing in physics right now, but it might be true. And then the universe out of nothingness, well, I would speculate, or I would posit that the idea of something out of nothing is, if not a natural idea, not an unreasonable idea for thinking brains to come up with, right? There are only a certain number of origin stories that you could have for the universe, and a quite obvious one, if you ask me, is that it came out of nothing. Another obvious one is that there's a divine creator, a supernatural being that created the universe. Okay, there's two possibilities. I mean, I'm hard pressed to think of many others, right? And so it's just a pretty obvious possibility that I wouldn't attribute to any amazingly insightful insights to either Buddhist philosophy or any other philosophy that happened to have the same possible conclusion. Again, without denigrating any particular philosophy specifically. Okay, yeah. Yes?
I'm curious, what are you observing tonight?
Yeah, what am I observing tonight? We're going to be observing exploding stars, mostly. And we're observing them with a technique that will show us, hopefully, whether they're exploding in an asymmetric way, spherically symmetric or oblong or whatever. And we do that by measuring whether the light is polarized or not. So, a little tiny 30-second detour here. What are polarizing or polarized sunglasses? Well, light from the sun is unpolarized. Electric field is oscillating this way, or parallel to the ground or perpendicular to the ground, are the two ways in which the electric field can oscillate if the light is traveling this way. And it turns out that when it bounces off of the ground, the component that's oscillating vertically is suppressed. It doesn't reflect as well as the component that's oscillating horizontally. So the reflected light from water or pavement is polarized. And if your sunglasses only let through the component that's vertical and not horizontal, well, you're cutting out most of the light that reflected, and in particular the light that causes the glare, because the glare is coming from the predominant light, and stuff. And so you're seeing just a small component. That's how, it's not that the glasses are polarizing, the reflection phenomenon polarized the light, and then your glasses are letting in the subdominant, direction of polarization. So anytime you have asymmetries you can get an enhancement of one direction of the electric field oscillating versus another, as opposed to a sphere where it's spherically symmetric. It looks the same from all directions, so no directions are preferred. So you get zero net polarization. Okay, so we're looking for a net polarization from these exploding stars at various times of their lives, mostly when they're young, because that's when they're bright, and you need to gather a lot of light to detect a tiny sub-percent, even 0.1% level of polarization expected from even pretty big asymmetries in the exploding star. I mean, you don't have anything nearly as asymmetric as light bouncing off of pavement or water or something. An exploding star is much more symmetrical than that, so you expect very low levels of polarization.
Is that through direct observation?
Through direct observations, yeah. Yes? Mm-hmm.
Is it fair to say that the logical probability is there are multiple universes, but however, we'll never know?
So is the logical conclusion that there are other universes, but we'll never know? Yeah, that's my point. That's what I pretty strongly believe, based on these lines of reasoning and the circumstantial evidence, of a universe that's much bigger, at least, than ours. At some level, well, okay, the one that's bigger, and we're just one observable volume, that one exists. And I think we have evidence because of this issue that we have measurements that show that the total universe is at least 100 times bigger, or more likely at least 100,000 times bigger. So that one, I think, in a sense, we've shown, which is why I would argue with conventional physicists we've sort of proven. Because otherwise, if not, then we're in the very center of all that there is. And how likely is that? That's another argument, right? For the totality of all that there is being bigger than just the part we see. If the part we see is all that we exist, then we are at the center. And out of the 28 billion light year, actually it's now 96 billion light years, if you take into account the expansion of space since the light was emitted. But what are the odds that we're in the middle of this 96 billion light year, or 92 billion light year, 46 billion light year radius volume? So I would claim that multiverse, where it's the same laws of physics and same constants of nature, but a bigger totality than our observable universe, that exists. But some physicists would say, that's what we mean by the universe. And that's why I was careful to say that there's our observable universe versus the total. Some physicists would say that the universe is just the observable universe, and they may disagree with the total being bigger. Others say, yeah, it's obvious, the total is out there and it's bigger, but that's what they already call the universe, and so they have no argument with me on that score. But they do have an argument with me about the multiverse, where it's the different laws of physics or the different laws of nature, right? That's where physicists have a greater disagreement. And there, I would say, I think they exist, the universes with the different physical properties, but we'll never know. Okay, did I clarify that? The really weird ones exist, but we'll never know. The one where it's just a bigger volume than the volume that we see, that exists, and we do know it, and few physicists would disagree with that. It's just that many of those say, yeah, that's what we already mean by the universe. But others would say, yeah, we agree, there's a bunch of volumes out there, and by the universe we mean our observable universe. That's why I was saying you have to be very careful in your discussion with a physicist to ask, what do they mean by the universe? Do they mean just our observable part, or all that there is? If they mean all that there is, and they say, yeah, that's fine, but that's what we already mean by the universe, fine. And then they say, Alex, your other universes are the crazy ones. And I think they're a realistic possibility, even a probability, but we will not know, ever. Yeah, okay, so, yes. I could have stated all that much more clearly, but I didn't. Anyway, go ahead.
I'm curious what your thoughts are on Dr. Penrose's theory about the role of quantum processing in consciousness, and if you subscribe to it, what role do you
Yeah, so there's this idea of Roger Penrose that consciousness and quantum processing are intimately related. So I'm absolutely no expert on consciousness. I don't know that anyone is, or even the brain, where there are people who definitely study the brain and what's going on. I'm pretty knowledgeable about quantum mechanics, though, and it seems reasonably far-fetched to me that consciousness is related to quantum processes. I don't know enough about Penrose's hypothesis. Frankly, I've had a hard time understanding exactly what he's saying. He's a brilliant mind. He did brilliant things. He won part of the Nobel Prize in Physics for his theoretical work with Stephen Hawking on black holes, okay? But in these last years, some of the things he's been saying are stated in a way that I've not found particularly understandable. That may be more a limitation of my limited mental capacities. But my suspicion is that consciousness is not related to quantum processes. And part of the reason, you might say, what's my reasoning? And there's a lot of things, but the simplest reasoning is that quantum processes are really pretty random. And consciousness, I can consciously think about scratching my head. This is where you can get into this very interesting discussion of whether there's any such thing as free will. And I used to defend free will. Of course there is. And I've been gradually moving to the camp, like Sam Harris and others have argued, and a number of physicists, that there is no free will. It's just we have the impression of free will. But everything we say and do and all of our actions are triggered by neural responses to previous actions. And those were triggered by neural responses to previous actions. And so then everything is determined from the Big Bang. And that bothers me a lot. Because it means that, on the one hand, we're not accountable. Right? I go and murder someone, which I'm not going to do, right? And I know that I'm not going to do it, right? But if I were to do it, I could then argue that, well, it was predetermined. Someone is going to be a collection of particles that kills someone. And so how can you then convict, especially with the death penalty, someone like that? But then you could argue, those that convict with the death penalty, there was no way they could have done otherwise because that was predetermined by the Big Bang, right? So the free will issue, I'm very torn on it, but I find it hard to argue with the logic that everything has a physical cause. If not, then it's a supernatural cause, and I will reveal my tendencies here that I think the universe is a physical universe, and that maybe there was a supernatural creation. I won't tell you what I feel about that. But after that supernatural creation, my own personal belief is that the universe is a mechanical universe. It just goes along like gears. And there are things that happen randomly as a result of quantum mechanics, but as a result of Hugh Everett wanting all of quantum mechanics to be governed by what's called the Schrödinger equation, whereas in conventional quantum mechanics, the act of measurement is not governed by the Schrödinger equation. It's like, the wave function collapse. That's Niels Bohr's and the Copenhagen interpretation. Well, I either scratch my head or I don't scratch my head. The cat is alive or dead, Schrödinger's cat, right? Hugh Everett says, no, there's a cat, when Alex opened the box, that is dead, and Alex saw that it's dead. And now there's another universe, equally real, where the cat is alive and Alex saw it alive. It becomes a quantum entangled double universe. But that's a very simple example. All the time, everywhere, everything is happening, and it could have happened differently. And Hugh Everett says that those are all real universes. And Sean Carroll, who has a very interesting book called Something Deeply Hidden, he's a very deep thinker and a very clear writer. I recommend that book, but he's a real Everettian. So I asked Sean, where the hell, if you pardon my French, are all these other universes? He says, Alex, they're in the Hilbert space, which is a mathematical space, possibly infinite, of all possible universes. And that just leaves me cold. Because I say, well, if they're all part of this infinite level 1 multiverse that inflated, let's say, for an infinite time, and then there's an infinite number of them, all having different physical conditions, or I'm sorry, all having the same laws of physics, but different initial positions and speeds of particles. So in some of them I scratch my head, and some I don't, and some of them I kill someone, but in most of them I don't, right? He says, I say, if the Everettian multiverse is the level 1 cosmological universe, then I'm game. And he tells me in no uncertain terms, no. The Everettian multiverse is not the level 1 cosmological simplest multiverse. It is a universe that is continually branching into the Hilbert space of all possible universes. And in all of those universes, you can use what's called the Schrödinger equation all the time. And maybe mathematically that's elegant, but I just don't buy it. But what's interesting is that if you ask card-carrying quantum physicists over time now, what they used to think and what they now think, not a majority, but a plurality of people who deal with this are now subscribing to the Everettian many worlds interpretation. And I just don't get it. But anyway, how do we get onto this? Consciousness, I mean, we make conscious decisions to drink or whatever, and there I just don't see the randomness of quantum mechanics tying in with that. Yes?
Okay, how about a non-philosophical question?
Okay, a non-philosophical question.
So you're well known as an astronomer.
Yeah,
Somebody
I'm
like
known
Neil
as an
deGrasse-
astronomer, astrophysicist.
Okay, that's the question. So somebody like Neil deGrasse Tyson is known as an astrophysicist.
Yeah.
Where's the demarcation, or is there any?
Where's the demarcation between astronomy and astrophysics?
Astrophysics, yes.
Astronomy and astrophysics. Yeah. At this point, there's essentially no difference between astronomers and astrophysicists. And I often say, and I'll explain for a moment, I often say I'm an astronomer, but then because I don't want to say I'm an astrophysicist because it sounds more pretentious. It's got more syllables. But I do worry, and I know Neil Tyson very well. He's an exact contemporary of mine. We're good friends. He's a marvelous spokesperson for science in general and astronomy in particular. And he definitely calls himself an astrophysicist. And I'm all, Neil, that sounds pretentious. And but he says, well, Alex, yeah, but you've certainly run into people who then hold out their palm and ask you for a reading or say, well, I was born when Mars was in Capricorn, and so who am I going to marry or whatever, Right, they sound similar, and they even have a common root. They were common thousands of years ago, but they've split apart. And so the general public often confuses astrology and astronomy, and for that reason, I understand why there's a preference to call oneself an astrophysicist. And so more recently, I guess I've been doing that a little bit more commonly, although our own department is the Department of Astronomy, and but our own students have asked us to give them a degree in astrophysics, which we decided to do because they found that they are more employable if they claim they have a degree in astrophysics rather than astronomy. So even big-time companies, tech companies, have employers among them who don't understand this difference or look down on astronomy a little bit, perhaps subconsciously because of its potential connection with astrology. So why were they largely the same long ago and not anymore? Long ago, astronomers would measure the positions of stars and brightnesses and their colors, and they would make catalogs and stuff with little attempt or little successful understanding of what the stars are, the relationships among them, what produced them, what's going to happen to them, and so on and so forth. They were essentially like botanists who were, those botanists who were interested in defining what kinds of plant species there are, which is the first step in coming to some understanding of them and all that. You want to categorize them. Petunias are not exactly the same as bamboo, as timber bamboo, okay? They're different. It's important to recognize their differences, okay? But now, almost all astronomers do attempt to achieve a physical understanding of the measurements that they are making, that they or others have made. And so essentially all astronomers are now astrophysicists, and the degree to which they use physics may differ. Theoretical astrophysicists do a lot more physics than while we're simply collecting photons as we will be tonight, although my team and I will be analyzing those photons for the coming year, probably several years, and then writing, we hope, research papers on it so we can get additional time and funding and all that kind of stuff, But there's not much of a difference anymore, essentially. Yes? Mm-hmm.
I'm actually wondering, where do your grants come from?
So where do my grants come from? Great question. Little advertisement, I'll give you $20 afterwards. So they used to come from the federal government, but the discretionary slice of the federal budget is becoming infinitesimally thin, right? And pure blue sky research of the type we're doing, which has very little obvious practical consequences, right? We're not making better pacemakers or toasters, we're not curing cancer and stuff, and there are arguably many important societal needs. And there's the national debt and things like that, right? The deficit each year, and there's the homeless, and there's all kinds of things, right? We've got to put a lot of resources into developing new forms of energy and stuff, and so it's not unreasonable to ask, why should the federal government spend any money on people like me? And I have, this elevator pitch, the short version of which is that we're the only animals we know of that can do this kind of stuff, so some subset of us should. This kind of stuff excites kids, most of whom will not become theoretical particle physicists or high-energy particle physicists or astrophysicists. They'll go on into fields where they're more employable and they're of greater immediate benefit to society, like engineers, applied physicists, medical physicists, computer scientists. But they get turned on by, the lunar landings, as I did as a kid, or the Hubble Space Telescope, or the James Webb pictures and things like that. So it's the butt that bites them. That pitch is slightly effective on Congress. The one where we're just Homo sapiens, they're like, forget that, I'm not going to give you any funding. And then there's the one where you never know what the practical spin-offs might be. And the example I most like to give is that a century ago, there were at least two main questions, but those relating to quantum physics were the nature of light and the stability of atoms. What is light, and why are atoms stable? It turns out they should be unstable. And you could say, well, as long as we can create light, and Thomas Edison did that by sending a current through a wire that had a certain resistance and stuff, and as long as tables don't collapse, who cares how they actually work, right? Why would you do that kind of work, okay, right? But quantum physicists worked on it, and we now understand light, and we understand the stability of atoms. And fast forward a century, and you get these devices with 500 million transistors on the head of a pin, right? And you get laser scanners, and you get your scanners in Safeway and department stores and things like that. You can't imagine today's life without an understanding of the nano world, the quantum world. So it's the unanticipated spin-offs. And in relativity, Einstein was thinking, how is gravity produced? And he has this crazy idea of the warping of space and time. And is this, even if it's true, just intellectual titillation for theoretical physicists? Well, it could have been, but guess what? 50 years after the development of general relativity, GPS was developed. And that requires not only special relativity, but general relativity, because to make it short, the satellites up there have clocks in them, but those clocks run at a different rate than the clocks down here. And the clocks are communicating with each other. And if you didn't take into account the faster rate in the weaker gravitational field, you would get the wrong answer. So GPS, with all of its commercial and military applications, is an unanticipated spin-off of Einstein's relativity. Well, those arguments, quantum mechanics and general relativity, fall on deaf ears in Congress because they're interested in being reelected, and you need to lower taxes, etc., right? And so these pie-in-the-sky spin-offs a century from now are of no interest to them. So our main line of reasoning is that it excites kids. But kids can get excited in other ways, they say. And there are many societal needs. And even though something like the Webb telescope cost every taxpayer something like one hamburger, it might have been a little bit more than that. Maybe it's one hamburger per year because it was $10 billion, but we could figure it out. Whatever, it's not much. But people go crazy when it comes around to taxes. And then you hear about studies that, to the typical person, it's like, why the hell is the government spending any money at all on this kind of research, right? We're sitting around, in fact, there's this huge wave turning against higher education overall and research in general, unless it's for very specific purposes like trying to cure cancer and stuff. So bottom line, I'm relying more and more on private donations. Individual people, families, foundations, in some cases corporations. So if you'd like to support me, or someone who wants to, then I can give you a different address than the Lick Observatory one, but here I tried to be more altruistic and not be in it only for myself. I am a user of Lick Observatory, my students are as well, so I will benefit from this, but not as directly in a sense as funding my own research. And so I'm very grateful that I have some friends who are very generous donors. But I have a lot of hungry mouths to feed, so I need more generous donors. But anyway, yeah, yes, right. Oh, well, let me see if there's any other people who haven't yet asked a question, and then if there's time while I'm putting away my equipment, I'll answer yours, because I do have limited time. Yes, go ahead right there.
For a couple of subjects ago, unfortunately, I was going to ask you if it was possible that consciousness is so slippery because it can't be recursive.
Is it possible that consciousness is so slippery because
It can't be recursive.
it can't be recursive? Yeah, maybe, but again, consciousness is way above my pay grade. I don't generally like to mouth off too much about subjects that I don't know much about. Right? So let me pass on that question, because I don't know anything about consciousness. Yes, over here.
I just want to say thank you for saying that even your brain hurts when you think.
Oh, my brain hurts. Yeah, the remark was thank you for saying that even that is, my brain hurts when I think about some of these topics. It definitely hurts. But I love thinking about these things because they really stretch the imagination and what our amazing 12-watt minds are capable of. 12 watts. In that sense, AI, as it currently is very different from what's actually happening in our brains. I think we're not just streaming together the next most probable word out of 100,000 based on zillions of digits on the internet, right? All the digitized books and articles and all the conversations people have had with each other, and et cetera, et cetera. So whatever the LLMs are doing, it's not what we're doing, but it may be a step toward artificial general intelligence. But I claim we're something really special, even if it does look like these things are beginning to mimic in a conversation, especially if you don't ask very sophisticated questions. I would claim the Turing test has already been passed. If you ask only simple questions, you cannot tell whether the thing on the other side of the opaque wall is another Homo sapien or a computer. If you're quite sophisticated, you can still tell. But they're getting close, and it's awfully scary. Someone who hasn't asked a question yet? Did you ask one yet?
No.
No, you didn't. Go ahead.
I was just thinking about the anthropic principle.
The anthropic principle, yeah.
And the physicists that object to it in terms of the universe. It seems in terms of the Earth, the Earth is well tuned for our life on it. And it seems pretty obvious, maybe I'm not thinking about it right, it seems pretty obvious that the anthropic principle applies there.
Yeah.
And so
I'll
if
rephrase.
it applies there to the Earth, why can't it also apply?
Yeah. So the question is basically of the physicists who dislike the anthropic principle, it seems pretty obvious that it applies to Earth, as given by the exoplanet examples, right? I mean, we now know that they have a vast range of properties, and we haven't even measured all their intimate properties. So why wouldn't it apply to the universe? I mean, it could. It's a plausibility argument, but their objection to the anthropic principle is, I find, even more puzzling. It's a selection bias. Here's the idea, right? If I observe a cell phone, it has to exist, right? The way I like to put it, if you gave a sufficiently well-educated baby, if you told a sufficiently let me try to, if you were to tell a baby that knows enough physics that we exist, okay, the baby could figure out that there has to be carbon and oxygen and things like that, not just hydrogen and helium. You haven't told the baby that we have carbon and oxygen and calcium and iron. You just say, baby, we exist, you exist, and you know the laws of physics, okay? But you don't know about the periodic table. The baby could reconstruct part of the periodic table given our existence, because hydrogen and helium alone don't form long bonds. And then the baby could figure out, oh yeah, neutrons come together with protons and they'll build up a thing. And they had to have in order for us to be here, right? So it's a selection bias. There are selection biases all the time when you do science. In fact, it's very important to be aware of what biases are in your project, because there are even things like confirmation bias, right? You have some hypothesis you desperately want to show that it's correct. That's sort of more fun than showing that it's incorrect. And so you tend to see the evidence that supports it and not see the evidence that doesn't support it. So there are all kinds of biases, but our existence, I have some better examples, but today, because I was sort of focused on the observations for tonight and thinking about it, I'm not thinking of them now, but okay. Knowing that we need air to breathe biologically, you can conclude that Earth has an atmosphere, right? That's anthropic reasoning. Oh, I know what I wanted to think of. It had to do with carbon. I knew it had to do with carbon. There was a physicist named Fred Hoyle who was famous and infamous. He did a lot of really great work, and then he started thinking about some pretty crazy things in his later years, and so he lost some credibility. But he, a long time ago, more than 50 years ago, 60, 70 years ago, he argued, based on quantum mechanics, that it's so unlikely for 3 helium nuclei to come together through nuclear fusion in the core of a star in its advanced stages of evolution, beyond what the sun is right now. It's very hard to get 3 helium nuclei to come together and fuse to form carbon. And then for another helium nucleus to come in and produce some oxygen. He says that's really, really hard. At too low temperatures, the carbon simply won't form. And if you raise the temperature, you can get the 3 helium nuclei to come in to form carbon, but it's very likely that another helium nucleus will come in and make that carbon into oxygen. So you'd have a whole bunch of oxygen, not much carbon. The roughly equal amounts of carbon and oxygen in the universe in terms of abundances is very strange. He said, that's really strange. I don't understand it. Unless there's what's called a resonance. When particles come together, they can stick together longer because of a resonance than you would have thought if they just are like billiard balls and collide off each other. A resonance in common terms is you've got a kid on a swing, and if you push them in phase, right, you can increase their amplitude. Whereas if you push them out of phase, you push them forward when they're going backward, you do all kinds of random things, their amplitude won't increase. That's a resonance. Or a tuning fork. You've got it vibrating, and you've got a bunch of other forks that vibrate at various frequencies. The one that will start vibrating is the one that's at 440 hertz or whatever, right? That's a resonance. So, okay. So Fred Hoyle said that there's a resonance in the carbon nucleus that makes it last longer than it would otherwise. And so at lower temperatures, you can get that form of carbon to form, and I think the way it goes is it forms in an excited state, and then it can decay down to the ground state, the lowest energy level, and produce some carbon, instead of having the things just bounce off, okay, almost instantaneously. Or you raise the temperature to such a degree that, forget about the resonance, 4 helium nuclei come together and you get a bunch of oxygen. See, there's a resonance that makes the carbon last long enough that it can then decay down to the stable form. And that'll happen at a relatively low temperature, 100 million degrees. Okay, Then he said to a Caltech experimentalist, Willie Fowler, who would measure nuclear reaction rates and what were called cross sections. Cross sections are sort of, if you have billiard balls hitting each other, but a billiard ball is actually bigger. It's like a basketball, then another ball coming along is more likely to hit it, right? So that's by cross section. If it's a ping pong ball, it's less likely to hit it. So for various nuclear reactions, you measure the effective cross sections. And Willie Fowler measured it, and lo and behold, the carbon nucleus has this state, this resonance, at essentially exactly the energy that Hoyle predicted. Within 0.5% or 1%, Hoyle said that if particles come together with a certain energy, generally they'll bounce off or whatever, but if it's a certain energy, there's this thing where it's like doing the kid at the right frequency and the right phase, and it'll last longer. And Willie Fowler measured it, okay? I claim that was an anthropic prediction because Hoyle said the roughly equal amounts of carbon and oxygen are very difficult to understand in the universe. There's this flight, it keeps bugging me literally. Unless there's something in nuclear reactions that makes it more likely for carbon to form. And he not only said that there's this thing that's going to happen, he predicted the energy at which it would happen. And it was measured to be true. That was an anthropically based prediction. Some of my physicist friends disagree, and some because they don't understand. They say something like, oh, just raise the temperature in the middle of the star and you'll get carbon. They don't understand that once you do that, you're more likely to form oxygen. So it's a thin balance, okay? But that's a pretty complicated example. Selection biases is just, we need air to breathe, therefore there's got to be air in our atmosphere, right? Okay, so there we go. Listen, folks, I've got to end at this point, but anyway, thank you very much. Yeah.
And most of all, I hope you'll give Dr. Filippenko another huge round of applause.
Thank you. And that's, in addition to truth is a great flirt, I now need to memorize belonging precedes believing.
I think it's true at least a little bit.
Email me that or I'll forget with my primitive mind. Belonging precedes believing. Okay, very good.